Hopefully everyone can see my screen. So today we're going to talk about statistics. All right, and let's review a little bit of what we went over last class, just to make sure we're feeling okay and kind of remember some stuff. So Carrie talked a lot about ggplot, which is a function in which you can specify data and variables and create a beautiful plot. Inside ggplot, you use this mapping AES to specify programmatically what you want to correspond to, like the X and the Y axis or group or color. Layers of plots can be combined with plus signs. So we've been using the pipe a lot to work with our data sets. ggplot is a little bit special in that it has the plus sign to kind of tack things on to the end. And among the things that you can tack on are geom line, geom point, to add lines and points respectively. Sometimes you need to add a grouping element just in case you have overlapping data, or your plot. We looked at some plots yesterday that looked a little funky. You may need to separate out by group. And of course, make sure you're plotting what you think you are, check your numbers, make sure you're using the right variable, if you've renamed your variables or something like that. And then facet grid, facet wrap can be helpful for splitting your plot up into different panes. It kind of makes things easier to look at sometimes. Okay, we also talked about factors. So factors allow us to have a different specified order. So we talked a lot about character data, and that just is words or text, but maybe we want to order it in some specific way other than alphabetical. And we can change data to a factor really easily using mutate or as factor, just a bunch of different ways we can approach that. And we can also reorder factors by other variables. So kind of nice, which is super useful for arranging, tabulating, plotting, because maybe we're interested in a specific order. And this helps us do that without having to do too much like manual, strong holding of our data before it goes into the plot. Okay, so for this module, we'll talk about just some really kind of commonly used basic statistics to fit some basic statistical models. We'll talk about correlation, t-test, and a few types of regression. And so very important that we're going to just focus really on how R does these, right? We're not going to dive super deep into the statistical theory, the assumptions, the formulas, and of course, whenever you get kind of into statistics, you have to think about the assumptions that you're going into it with. And we're not claiming that the data we're using meets all of those assumptions. So, please don't go to your next course and be like, well, Ava and Carrie did this and said this was fine because the data looked like this. So just be aware that, you should think about the assumptions of the tests you're using. And we, of course, have dedicated biostats courses to learn more about the statistics and the theory behind it. And I just want to point out, Carrie is part of this project called Open Case Studies, which does deep dives on some of the concepts here. So if you really want to learn more about like the nitty-gritty behind linear regression, I definitely suggest checking that out. They're all public health focused data sets. So it's kind of a nice way to do some actual applied analysis. All right, let's jump into correlation. So the function core, very straightforward, computes correlations in R. And these are the arguments that it can take. But generally, we're providing core with two numeric vectors, argument X and Y. So item 1 and item 2. Okay. And so it would calculate the correlation between those two vectors. You can also provide a data frame or tibble or several columns of a data set and calculate a correlation matrix among all of them. And just generally by default, correlation uses a Pearson correlation coefficient. So calculated slightly differently, but if you'd like to do a different approach, maybe a non-parametric approach, you can pick a different method. All right, so let's just jump in and kind of see how this works. So we'll use the circulator data set, and you can load it doing this. So I'll go ahead and bring that in. Okay, and so remember that I have my different bus routes. I have the getting on the bus, getting off, and the average for a bunch of different bus lines, different days of the year, days of the week, etc. Okay, so like I said, we compute correlation by providing two vectors. And like other functions, our mean, our median, things like that, if there are NAs, we'll get NAs as the result. But if you specify using only complete observations, we can get the correlation of just the complete comparisons, right? So if we were to specify, okay, well, I want to pull out the orange average. So X is circ pull orange average, and Y is circ pull purple and I run core of X and Y, I get NA because as we recall, there were a lot of NAs in this data set, just days of the week that weren't collected for some lines. But we can add this use equals complete obs. And it's just going to use the lines of data where I have both numbers for both columns. Okay, so I would say that that's kind of correlated, right? So any value closer to 1 or -1 indicates that that they're maybe correlated. Okay, and just because I'm kind of visual with thinking about correlation, we can look at it also in plot form. So taking the circ data set, piping that into ggplot, using our mapping aesthetics of X is one of these lines, the orange line, and Y is the other line, the purple line. And of course, adding our geom point. The size is just to make it a little bit smaller so it doesn't clutter the screen. But yeah, you can see it kind of orange, the orange ridership kind of is related to the purple ridership, and that they have kind of what appears to be a relationship here. Okay, so we can also do correlation matrices. We don't just need two vectors. We can compute correlation for all pairs of columns of a data frame matrix, just basically something with columns. Columns have to be numeric, right? You can't correlate some kind of factor, gender or something that is categorical. The education we talked about, what would be the correlation of middle school and high school to some numeric value? I'm not sure. So you can't do that. But that being said, we can take the data set, we can select, use our tidy select here to select all columns that end with average. And so what does that look like? select ends with average, right? I'm just pulling out these columns that, exactly what it sounds like. It ends with average. And I'll pipe that or save that as a subset. And then calculate my correlation matrix based on those 4 columns, okay? And so what I get is a nice little grid like this, okay? So piping it or putting it into the core function just like we did before, putting that subset data set into the first argument, and then just letting it know I want to use complete observations because we had lots of NAs. And like I said, we get this nice little matrix. On the diagonal, I get 1s because the correlation between orange average and orange average should be 1, right? They're the same variable. But then I can kind of do pairwise comparisons. I can look, okay, what's the relationship between orange and purple? Okay, what's the relationship with green? And get a little bit more information that way. Okay, so if you've started your project, you'll notice that we'd like you to do some visualizations. And one really nice, straightforward one is a correlation plot that comes from the core plot package. So of course, you'll have to install that if you haven't already. But it's really straightforward to kind of plug in a couple of numeric columns and get a really nice plot and really nice, quick visual assessment of your variables. So taking that correlation matrix that we just made in the previous slide, this right here, putting that as our first argument, and then providing a little bit more information. So I'll also want to tell it, I just want the upper triangle, right? I don't need the information below because it's redundant, right? Like this number is the same as this one's the same as this one, right? So here I'm just taking the upper triangle above the diagonal, and I want to order them in a way that kind of makes sense to me. So we're doing a hierarchical clustering. Okay, and so I get this really nice plot here. And so right away I can kind of see, all right, well, if I'm looking at the banner line, the correlation with the other plots is a little lower versus green, orange, and purple kind of seem like they have more in common. Okay, so that is correlation, pretty straightforward. We're going to use the core function for that. And you can make really nice visualizations with the core plot. Okay, so let's move on to some tests. Maybe get some p-values here. So the t-test, the commonly used t-tests are 1 sample and a 2 sample t-test. And so a 1 sample t-test, we're looking at testing the mean of some variable or some vector to 0, right? We want to see if it's different. Or we can do a 2 sample t-test to test the difference in means between 2 groups. Okay. So the way we do that in R is just t.test. Again, pretty straightforward, not a complicated function. And we provide a couple of different arguments to it. So if we provide or want to do a 1 sample t-test, we can just provide X. If we want to compare 2, we can provide X and Y. And we can give it a hypothesis, right? So we have an option to do a 2-sided test. So whether we don't want to assume, if we're comparing 2 groups, we don't want to assume that it's the second group is greater or less than. So we want to have both options. Or if we have some information, we're saying, oh, I want to test that this second group is less than the first group or greater than. So we have options for our alternative hypothesis. So let's kind of see how that works in practice. So as I said, the one sample t-test, testing the mean of a variable just in one group. And by default, kind of has a couple of things that it does. So if we don't specify, one sample tests whether a mean of a variable is equal to 0. So mu equals 0. You can specify if you want a different one. By default, we're using a two-sided alternative hypothesis. And when we're looking at the output, the result is assuming a confidence level of 0.95. And, maybe you're interested in kind of a different output. If we just jump down here, you can see there's a 95% confidence interval. Maybe we want 90, or maybe we want 99 or something like that. So we can specify that as well. Okay, so let's do a little experimenting here. So we already pulled out this orange average, that's X up there. And let's just drop it into t-test here. Okay, tells me a little information. It's a one sample t-test. The data is X. And it tells me, it says alternative hypothesis true mean is not equal to 0. And remember that mu was 0 by default. Okay. And I can look at my t-statistic. That's really high. My degrees of freedom is pretty high. And my p-value is super low. So it looks like I can be pretty confident that there's evidence that this alternative, or that we can reject the null hypothesis, right? That the true mean is equal to 0. So that makes sense, right? When we looked at our average ridership, there were not a lot of days that had 0, right? And there were days that had thousands of riders, right? So makes sense that the ridership is not 0. Maybe the mayor of Baltimore is like, okay, well, I want to double check that there's not bus routes that have 0 riders. We could be pretty confident in saying that there are not 0 riders on this route. All right, and so maybe you want to not compare to 0, but you want to compare two groups. So you could do two-sample t-test for that, which, so a two-sample t-test is going to test for the difference in means between two groups, okay? And so it's testing whether the difference in means is equal to 0, right? Are they essentially the same? Because it's looking at a difference this time. And it's by default using a two-sided alternative, so could be greater than, could be less than. By default, confidence level of 0.95 or 95% confidence interval. It assumes data are not paired, okay? So we don't have before and after or something like that. And it assumes that the true variance in the two groups is not equal. Okay. All right, so don't have to kind of go to R to show you this, but again, I'm pulling out two vectors here and plugging them into t.test, one group followed by the other. And it tells me, okay, well, now I'm doing a two-sample t-test. I'm comparing X and Y, gives me a statistic, p-value, the hypothesis, all that good stuff. Okay, so you may be thinking, this is nice and all, but maybe I want to extract the p-value or extract the t-statistic for collecting and sending out to a CSV file or something like that. You can use the broom package, which has this function called tidy that can organize your results into a data frame, and you can print that out and use it later. Just nice to have it in table or tibble form. So to do that, make sure you load the broom library and install it if you haven't. But let's go ahead and run t-test. Oops, I need a parentheses there. All right. And we'll save that output as result. Okay. And so a result is just this printed text, right? But we can put that into the tidy function and get a nice table out, right? And you can see that the statistics, all that good stuff is the same. Okay. So just kind of handy. Okay, and so important concept, and just want to make sure you all know how to do this. But you run an increased risk of false positives or type 1 errors when you're doing multiple hypothesis testing, right? So you're doing lots of statistical tests. You run the risk of detecting something that may be significant just by chance, right? And so we want to avoid that. And so one thing that we do commonly to avoid that, in addition to just like being mindful about our experimental design and our approach, so we're not p-hacking, we can use the p-adjust function on a collection or vector of p-values. And so you can use a bunch of different methods, but it's again really straightforward. So if I have p-values 0.049, that might look familiar to some of you. I feel like often it's right on the cusp. And 0.001, usually we consider 0.31 non-significant, and a really low p-value here. But I want to take that and I can plug it into the p-adjust function in my p-values here. And let me tell it, I want it to do a Benjamini-Hochberg adjustment, okay? And so you'll notice down here that these p-values it spits out are a little bit bigger, right? So it's adjusting for the fact that you've done multiple testing and that those p-values might not necessarily be as low as you think they are. And of course, you can do a bunch of different methods. So maybe you want a more conservative approach like a Bonferroni adjustment. Okay, so we definitely don't have time to dive into all the types of tests you can do, but just wanted to throw it out there that if there's a specific test you want to do, there's statistical theory behind it, chances are R has a function for it. A lot of these are base R, but you can extend like pretty specific kinds of model design and all that kind of stuff using specific packages. So a couple more you might be interested in are, Wilcoxon test, Shapiro test, Kolmogorov, Smirnov test. Maybe you want to test for differences in variance, and maybe you want to do a chi-square test to compare proportions, or maybe even analysis of variance to kind of look for the difference between groups. So a bunch of these, may end up being useful for you. Okay, so with that, let's jump into the lab and we'll get some practice. All right, so let's talk a little bit about regression. Okay, so linear regression is basically just another modeling approach, a modeling method to look at the relationship between some kind of response, some kind of dependent variable, and one or more explanatory variables, so our independent variables. Okay. So we'll go over a little notation here just so we can kind of see how that translates into R. So when we think about a regression, we think about some response, some outcome, Y, as our dependent variable. And that's a function of this alpha, which is our intercept, beta, which is our slope, some kind of predictor, some dependent variable, and some kind of error or residual variation, right? Something that's not explained there. So these are things to note. So again, Y is the outcome, alpha is the intercept, beta is the slope, X is the predictor, and epsilon is the error. Okay. So I think, again, it's easier to kind of look at this visually. So if we have some relationship between an X and a Y variable, our alpha is our intercept. So where does the line intercept? 0. Our slope is denoted by the change in, basically going back to our math, right? Rise over run, to figure out kind of how that relationship's changing. And then error, how far away are those individual points from the regression line? Okay, so this is the same slide, but thinking about the response with one or more. So this time, let's add another explanatory variable. So what does that look like? Instead of just one explanatory variable, what does it look like to have two? So very, very similar. We still have our slope, we still have our outcome, but this time we have multiple slopes. So beta 1, beta 2, beta 3 are our different slopes, and x1, x2, and x3 are our different predictors, right? So instead of just one predictor, we have 3 in this case. Okay. So yeah, just a little bit of notation will make our lives a little bit easier later, but we're not going to go too much into why this is the way it is. Okay, so to fit a linear regression model in R, we'll use the function GLM, which stands for generalized linear model. And generally, you provide 2 arguments to the GLM function. So you'll provide it a formula, which is the model, basically this, right, translated into a way that R can understand. And that will be using names of columns in our data. And we also provide the data. So this could be a data frame, tibble, basically something with rows and columns. Okay, so let's talk more about this formula argument. When we're thinking about regression, this is what our model will look like. We've got our intercept and our slope and our predictor and all that good stuff. In R, this is really easy. It just translates to the outcome or the dependent variable, this tilde character, and any of the predictors. Okay, so I don't need to worry about kind of writing these out, the intercept and slope, because R will determine that for us. Okay. When we're putting this into our code, X and Y are replaced with the names of the columns from our data set. So let's say, for example, we're fitting a regression where outcome is the income for a particular person, and predictor is years of education. So in our GLM function, that formula would look like income as the dependent variables, the outcome, and our predictors are years of education. Okay. Okay, and same thing if we are using multiple predictors. So this model up here where we have 3 different independent variables or predictors translates into our as this outcome y with predictors x1, x2, and x3. And I just denote the same symbol here, right? It's just a plus sign to indicate that there's another predictor here. And again, in practice, these are replaced with the names of our columns from our data set. And so using the example before where income is affected by years of education, maybe we also think age and location could predict income. So we could just add those in using the plus symbol and then the name of that particular column. And again, R will figure out that intercept and these different slopes for us. Okay, so let's do a little bit of practice. Let's use data about emergency room doctor complaints. So just a little bit about this. Data was recorded on 44 doctors working in an emergency service at a hospital, looking at the number of complaints received and some other things like visits, whether they were a resident or not, what their hourly pay is, and how many hours they worked. And so if you want to follow along, this data set comes from the faraway package. You can load that with library is faraway. So let me scrunch this down just a little bit. I'm going to add a new chunk here. Okay. And the way you load this data is just a little bit different. You can do data, ESD comp, and then just type in the name of the data set because this loads an object automatically in your memory, in your environment. Oops. So if I do data, ESD comp, it's already producing that object. Okay, so got my data set here. Okay, so let's say we want to fit a linear regression to model the number of patient visits as the outcome and the total number of hours worked, this is the hours column, as a predictor. So let's kind of see how that works out. So we'll use the GLM function. And again, we want to use the column names for our formula. And you can specify formula. And let's say, okay, the outcome is the number of visits. And that's going to be modeled as an outcome of hours. Okay. And GLM doesn't know off the top of its head that you want to use the ESD comp data set. So we'll need to specify data is ESD comp. Okay. All right. So we can run that. And like I said, our guess is the intercept, our guess is the slope. It gives us that, gives us the degrees of freedom and a little bit other additional information. So this isn't quite as much information as I would like. So we'll talk about ways to get a little bit more from it, but let's go ahead and call this fit and save that. All right, so we talked a little bit about the summary function, I think, very early in the class, but this is super useful for looking at the outcomes of a model fitting. So we'll use the summary function on this fit, and we can get the estimates, of course, the slope, we can get the standard error, a t-statistic, and a p-value for that slope. Okay, so if I just do summary fit, I get a lot more information. So what this says to me is that, yeah, maybe hours worked is a pretty good indicator of the number of visits a doctor had. So that makes sense. You work more hours, you can see more patients. Yeah, so that all seems good. Okay, so let's try adding another explanatory variable to our model, maybe the dollars earned per hour by the doctor. So this doesn't change very much. I'm just taking the formula and I'm going to add revenue to it. Okay, and let's run this again. All right, and so you see that this output is a little different this time, right? I have different slope estimates for different predictors, right? So it's telling me, okay, well, both of these probably are important for predicting visits or for explaining variation in visits. Okay. Okay, so we've looked at numeric columns so far, but factors get special treatment in regression models. We can use factors, which are, of course, important in our data. But it's important to note that your lowest level of your factor, the first thing that you list out, your first level, is the comparison group, and all other factors are relative to that group. Okay, so if we're looking at the column residency, it takes on values of yes or no, right? Looks like it's a binary variable here. Okay, and because this is a factor, right, we're looking at instances where residency is yes, but we're comparing that to a baseline of no. And maybe we had maybe like the year of residency or something like that, and the first year was our first level. Everything would be in comparison to that first year. So second year, third year, or like an additional fellowship or something like that would be in comparison to that first year. So we can just tally this up like we've been doing before, but just to give us an idea of the different counts in each category, we've got 24 no's, 20 yeses, but yeah, it just looks like there's those two values for the factor residency. Okay, so when we plug in a factor into our regression, what does that look like? So let's go over here and look at it. So maybe we have an object fit 3 with GLM, and I'm going to have visits be predicted by residency. And again, I want that data to be ESD comp. Okay, run that and look at the fit. Okay, so this looks a little different. So what we have here is not just the column name, right? But we have a specific level. So we're looking at the effect of that level of the factor and seeing that it's maybe not significant at the alpha that we specify. But if we had other levels of this factor, they would also appear here. And the thing at the very end would indicate the level of the factor that it is, okay? So if we had multiple levels of this residency factor, we would see multiple lines here, even though technically we only have one predictor. Okay, so GLMs are really nice. This GLM function is great because it allows us some flexibility for fitting regressions for basically non-continuous or normal or linear outcomes, right? So we could also do a logistic regression or Poisson regression. And so the way we do that is by adding one more argument to the GLM, which is a description of the error and the link function to be used. So if we have a logistic regression, for example, we would use the binomial logit link. And you can look at more information about the family using the question mark family documentation for understanding more about that. Okay, so let's look at a slightly different data set to look at logistic regression. And so this was data collected on predictors of breast cancer malignancy. So this is the WBCA data. I know we're doing a lot of different data sets here, but we want to get a good variety of tests. So we'll do data WBCA, and it would help if I also spelled it right. Okay. So let's take a look at that. We've got this column on the left, which is class. And I believe 1 is means that it's malignant and 0 means that it is not. Okay, but we'll confirm that in just a second. Oh, okay. All right, so class is a 0, 1 valued variable indicating if the tumor was, I had that backwards, I'm sorry. 0 is malignant and 1 is benign. Okay, so maybe we're interested in trying to figure out what kind of predictors would predict the malignancy or the benignness of the tumor. And this is a binary outcome, right? And so logistic regression is an appropriate approach for this. Okay. So how would we run that? It's the same function and same kind of overall structure. We're taking a response variable as a column name. And maybe we're interested in using this cell shape and cell size to predict malignancy. Okay. We'll also need to specify the data. And this time we have to also add a family argument. Okay. And because this is a logistic regression, we'll want to do binomial. Okay. All right. Let's give this a name, and then we'll do a summary. Okay, run that. Oh, U shape not found. I used the wrong column name, so it's no E on the end there. Whoopsies. Okay. So yeah, very, very similar output to read. We get estimate for the slope there and intercept and all that good stuff, and p-values, standard error, all that good stuff. Okay. Okay, and then finally, I know that many of you are interested in kind of contingency tables and calculating odds ratios. So we'll do a kind of a toy data set here. So I thought this was kind of fun. This particular data comes from a data set from like the 1940s and people getting gastrointestinal distress. And apparently ice cream maybe wasn't as well regulated back then. But we're looking at whether this outcome of illness or distress could be a factor of eating ice cream previously in the day. Okay. And so if we kind of tally up this data we have here using count, so there are folks who were not ill that either didn't or did eat ice cream, and tells us like how many there are. And then folks that were ill, whether they did, so they did not eat ice cream, or whether they were ill and ate ice cream. So it's a combination of those two variables, and we can make a contingency table out of that. Okay. So it's really easy to do the odds ratio from that using the odds ratio function from the epitools package, and we may need to go ahead and load that and install it. But it's pretty easy. It's much like a t-test. So all we have to do is take the data set, pull the column for the disease outcome or symptoms or something like that. And then the predictor, which in this case was exposure or having eaten a particular item. And in the odds ratio, we'll want to give the predictor first and the response or disease second. And then we can see it puts this nice contingency table together for us where we've got the ice cream down here and then the outcome of illness over here. And it's telling us that the odds ratio is actually pretty high here. So the odds of illness in the presence of ice cream being kind of higher than the odds of illness in the absence of ice cream. So kind of a nice way to do that is pretty straightforward, but you do need to load a special package to do that. Okay, just some final thoughts before we kind of take a little bit more time to practice. So it's a researcher's responsibility to understand the method that you are using. You need to understand those assumptions and think about how you're interpreting those results, right? So the power is in your hands, but it is your responsibility to kind of know what you're doing. And it's also your responsibility not just to understand the theory and the method, regression, t-test, all that, but you need to understand the R software as well. Are you using the right arguments? And is the output, are you interpreting, the kind of arguments that you're giving it correctly? So, by default, a t-test does a two-sided test, but is that an okay assumption, right? And just knowing that those defaults exist. All right, so let's summarize really quick. We can use the core function to calculate the correlation between two vectors or multiple columns of a data frame. And core plot is really nice to quickly visualize multiple correlations if you're taking them from numeric data columns. T-test looks for the difference in means between two vectors, so you do need to pull those out. GLM can work directly on a data set. We need to specify a few things though. So we need to use the formula argument to specify the model, which would be y tilde x or y tilde x1, x2, whatever, but using the column names. We use the data argument to indicate the data set and the family argument, and in particular, you may use binomial a lot to do a logistic regression. But yeah, the family will help you do other kinds of regression. And then doing summary on the model fit gives us more useful statistics than the output of GLM alone. Odds ratio from the epitools package can calculate odds ratio from your contingency table. Can be kind of handy if that's the kind of data you're working on. And then finally, this is just the tip of the iceberg, right? There's a lot of functions that you can use to do all kinds of tests. And sometimes it just takes a little bit of searching or maybe even diving into a paper from a colleague and kind of seeing what packages they used, what R code they used. Because yeah, I mean, it's your subject area experts and you know the literature, right? You know what the accepted approaches are, but maybe you want to apply them in R.